So today we begin the discussion of complex valued sequences. So first recall what is a sequence. So a sequence is a function from the natural numbers to any space x. In this case, our space is going to be the space of complex numbers when we're talking about complex numbers. And sometimes we use the letter r to talk about real valued sequences. So the sequence will then, in other words, operate on elements like f of 1, f of 2, f of 3, etc. And each such value is going to be a complex number. In general, you write f of n equal to xn, where xn is the nth number of the sequence. And that is common to denote a sequence by simply writing x sub n, where n goes from 1 to infinity, or by listing it as a ordered tuple. So here is x1, here is x2, here is x3. Somewhere along the line we get xn. And since it's an infinite sequence, it continues in this fashion. So you can see that from this ordered tuple, you can read what the function is doing. It's mapping the number 1 to x1, the number 2 to x2, the number 3 to x3, etc. So a sequence is said to have a bounded range. Well, first let's say what the range is. So the range of the sequence xn is defined to be the set A, which is equal to all the xn, where n is bigger than or equal to 1. So this is just the set of all possible outputs. We're going to shortly present those examples. So a sequence is said to have a finite range if the number of elements in A is a finite number and infinite otherwise. The sequence is said to be bounded if there exists a number m in R such that the absolute value of xn is smaller than or equal to m for all n. So the absolute value of each of those numbers is smaller than some fixed positive or non-negative number. So let's look at a few examples to make this definition clear. So let's look at example A, where our sequence is 1 over n, where n goes from 1 to infinity. So this is a complex valued and in particular a real valued sequence. The outputs are, you can also list it as 1, 1/2, 1/3, onwards. So we know that, we know it from calculus and from previous lectures, that limit as n goes to infinity of 1 over n is equal to 0 in the regular absolute value metric. So that implies that 1 over n is convergent. 0 with respect to the absolute value metric. This sequence is bounded. Why is it bounded? Well, if you take the absolute value of each 1 over n, it is less than or equal to, say, the number 1. So that is true for all, the symbol means for all n. This is an infinite sequence. More precisely, the sequence has infinite range. Because the outputs are 1, 1/2, 1/3, there are infinitely many outputs. The set A, which contains all the 1 over n such that n is bigger than or equal to 1, this set contains infinitely many elements. Now let's consider another example. So example B, let's suppose that we are given a sequence xn equal to n squared. So the sequence can also be written as 1, 2 squared, 3 squared, etc. So looking at the sequence, it is clear that that it is unbounded. So the sequence is unbounded because there is no greatest number. That follows from the Archimedean property. So there is no largest, there is no number for which all the terms of the sequence are smaller than it. And this sequence is not convergent. Again, not convergent in R. The metric R absolute value, as we spoke of general sequences. And the range is infinite. Here is one other example. Suppose that we have xn given by 1 plus minus 1 over n. So this sequence is convergent. So you can say xn goes to 1 as n is going to infinity, so it converges. As soon as you know that the sequence is convergent, that right away tells you it's bounded. Without trying too hard, you can see that each xn is smaller than or equal to 2. By the way, I should have said minus 1 to the n. Yeah. So it's bounded, it's smaller than or equal to 2, and it has infinite range. because the outputs are 1 minus 1, which is 0. 1 plus 1/2, which is slightly bigger than 1. That's why I said less than or equal to 2. And considering in this fashion, you would see that you have infinitely many outputs. So consider another example. Those, the previous sequences were all real valued sequences, in fact. But this sequence so xn is equal to the number I raised to the power of n. And I is, as you remember, root of -1. So that now it is a complex valued sequence. So what can you say about the sequence? So you have x1 is equal to I. x2 is equal to I squared, which is -1. x3 is equal to I cubed, which is -I. And x sub 4 is equal to I to the power 4, which is going to be equal to 1. x5 is going to now again be equal to I. x6 is going to be equal to -1. x7 is going to be equal to -I. And x8 is going to again be equal to 1. And it cycles through those positions. So it's clearly that the sequence, it's clear the sequence is not convergent. And again, we talked about convergence in previous lectures, so not convergent in C absolute value relative to the space C and the distance function absolute value. The sequence is bounded. So if you take any xn, that is absolute value of I to the n, you find out that all those numbers are just of size 1. So that's less than or equal to 1. So it's bounded. And has finite range. Sequence has finite range. Because the set A, which is I to the n, where n is bigger than or equal to 1, is just the set I minus 1 minus I and 1. So you can see that there are only 4 distinct outputs. Maybe one more example. So this is example E. We can take the sequence xn to just be the constant sequence. So it's always equal to 1. So that means that we have 1, 1, 1. For each place in the tuple, the output is 1. So the sequence is convergent. It is clearly bounded and has finite range. In this case, the range is just a singleton point 1. So now perhaps we talk about the limit laws that hold for sequences. So here is that theorem that you have learned in calculus, and this theorem is still true for not just real valued functions, but also for complex valued sequences. So suppose we have a sequence Sn and sequence Tn. So they are complex valued. And we have that limit as n goes to infinity of Sn is equal to S. And we also have a limit as n goes to infinity of Tn equal to T. Then we have that limit of the sum is the sum of the limits. We have that limit as n goes to infinity of C times Sn is equal to Cs for all constants C belonging to the complex field. Also, by the same rule, we also have that limit as n goes to infinity of C plus Sn. That actually follows from part A, where C is taken to be the constant sequence. That was just C plus S. See, we have that limit of the product is the product of the limits. And D, the limit as n goes to infinity of 1 over Sn is going to be equal to 1 over S, provided S is not equal to 0. So let's establish those results. Proof. So let's prove part A, which you recall we are showing that limit as n goes to infinity of Sn plus Tn, that is just the sum of S plus T, where the limit of Sn is S and the limit of Tn is T. So that follows by the delta epsilon. So we have part I, we have that Sn goes to S, and that implies that Sn minus S is going to be smaller than epsilon over 2 for n bigger than or equal to some number and 1. So in other words, if the terms of the sequence approach S, then eventually the distance between S and Sn is going to be very small, arbitrarily small. In particular, if I pick a number epsilon, it will be arbitrarily smaller than epsilon over 2, starting from some number and 1 and onwards. And 2, we know that since Tn goes to T, that implies that absolute value of Tn minus T is also going to be made less than epsilon over 2 for n bigger than or equal to some number and 2. Those numbers are natural numbers. So starting from some term of the sequence onwards, it's going to be arbitrarily close to T. Starting from some and 1 onwards, S sub n is going to be arbitrarily close to S. So now we know that Sn plus Tn minus S plus T by triangle inequality is going to be less than or equal to Sn minus S plus Tn minus T, and each of them is going to be smaller than epsilon over 2 if little n is bigger at the same time than n1 and n2. So if little n is bigger than or equal to max capital N1, capital N2. And this equals to epsilon. So this establishes that the sum Sn plus Tn is arbitrarily close to the sum S plus T, which proves that A holds. Proving B, proof is very trivial. That means you should do it yourself if you don't see it. So now let's prove C. Let's prove that limit as n goes to infinity Sn times Tn is the product of S and T. So the first thing to observe is that Sn times Tn minus S times T can be written as Sn Tn minus Sn times T plus Sn times T minus S times T, which we can now write as Sn times Tn minus T plus T times Sn minus S. And this we can write as Sn minus S plus S multiplying Tn minus T plus T times Sn minus S. And when we simplify the entire thing and factor, we obtain Sn minus S times Tn minus T plus S times Tn minus T plus T times Sn minus S. That's the formula we use. And then we observe that we can make Sn minus S arbitrarily small. We can make it in particular smaller than root of epsilon if n is bigger than or equal to some capital N1. And similarly, we can make Tn minus T smaller than root epsilon if n is bigger than or equal to some capital N2, where that's just the integer from which it starts. So what we can then do is, we know that absolute value Sn Tn minus St is going to be less than or equal to, well, let's actually first, just so that nobody is confused, write equal to our identity formula. So remember, we were able to write Sn Tn minus St as Sn minus S Tn minus T plus S Tn minus T plus T Sn minus S. And now we can apply the triangle inequality to each part, so we can say this is less than or equal to the absolute value of Sn minus S times absolute value of Tn minus T plus the absolute value of S times Tn minus T plus the absolute value of T times the absolute value of Sn minus S. Now this is going to be less than root of epsilon times root of epsilon plus absolute value of S times root of epsilon plus absolute value of T times root of epsilon if n is bigger than or equal to the maximum of capital N1, capital N2. So remember, when little n is bigger than N1, Sn minus S is less than root of epsilon, and when n is bigger than capital N2, Tn minus T in absolute value is smaller than root epsilon. So whenever n is bigger than the maximum, both conditions hold. Now what's this? This is just epsilon plus absolute value S root epsilon plus absolute value of T times root epsilon. And we can take epsilon to be smaller than 1, which implies that well, this is actually I suppose not necessary. So if you look at this quantity, this quantity is arbitrarily small. Arbitrarily small. So if epsilon is small, then this quantity is arbitrarily small. It can be made smaller than any number. That implies that this sequence converges to ST. So that completes the proof. So let's now prove D. Now we prove identity D, namely that limit as n goes to infinity of 1 over S sub n minus 1 over S is going to be equal to 0 if S is not 0 itself. So first observe that the difference 1 over Sn minus 1 over S is simply S minus Sn divided by Sn times S. And on the top, you can just rearrange it and write it as Sn minus S divided by absolute value Sn times absolute value S. The top part goes to 0, so all we need to do is establish that absolute value of Sn is bounded. So observe that absolute value of Sn minus absolute value of S is put in absolute values is less than or equal to Sn minus S. And this thing then is eventually less than 1/2 absolute value of s. So what I mean by that is that this number goes arbitrarily small. It becomes arbitrarily small for large values of n. And absolute value of s is a non-zero value. So eventually, for large enough n, Sn minus s can be made less than 1/2 times absolute value of s. So we can do this. So that implies that absolute value Sn minus absolute value s is going to be between 1/2 s and bigger than or equal to minus 1/2 absolute value s. And that means that Sn is less than or equal to 3/2 s. Again, what I'm doing, I'm just taking minus absolute value of s and I'm adding to it absolute value of s to cancel it here. I'm taking absolute value of s and therefore moving it across the unequal sign. Whereas here it's going to be just 1/2 absolute value s. And what it implies is that absolute value Sn is bigger than or equal to 1/2 s for a suitably large n. So that means that 1 over absolute value Sn is going to be smaller than or equal to 2 divided by absolute value s. So having this information, we can then say that this here is less than or equal Sn minus s divided by absolute value of s is just going to be replaced by, multiply this by 2 and divide by s. In other words, I just replace 1 over Sn by 2 over absolute value of s, and here is an extra s. And this number then can be made less than 2 times epsilon divided by s squared, which is an arbitrarily small number. So since this is arbitrarily small, this implies that this thing in the absolute value is arbitrarily small and therefore goes to 0. So that completes the proof of part D of this theorem. The next topic I'd like to go over is upper and lower limits. This is a very important topic for analysis in general. So hopefully later on, when we talk more about sequences, I will show some applications of the concept to be illustrated. So notice that some sequences are well behaved. So what do I mean by well behaved? So for example, you have the sequence 1 over n. It is well behaved because look what it does. So you have first term is 1 and the next term is smaller, it's 1/2. And 1/2 is smaller than is bigger than 1/3, and 1/3 is bigger than 1/4 onwards. And this sequence is gonna decrease steadily to 0. So it's a decreasing sequence. Those are called monotonically decreasing sequences. So that's a very well-behaved sequence. It is decreasing and it is convergent. Other sequences are not well-behaved. So you can take plenty of examples of non-convergent sequences. A terrible type of sequence might be sequence of the form sine n. So it's very difficult to read the behavior. So it will be sine of 1, sine of 2, sine of 3, onwards. The sequence, in fact, does not converge, and it's just gonna be scattering values in the interval -1 to 1. So this is a very poorly behaved sequence. It's neither monotonically decreasing nor monotonically increasing. It doesn't have the decreasing behavior or an increasing behavior. It does not converge. Right. So let's maybe record this. Not convergent. Not convergent. Does not decrease. Or increase. In general, you can say chaotic. It's a chaotic sequence. You can try by plugging a bunch of values in your calculator or better simulate it on the computer, and you will see that it does not have a nice pattern. So in real valued sequences, for real valued sequences, it's important, real valued. We just talked about generally complex valued, but for real valued sequences, it is always possible to, I'll put it in quotation marks, extract a nice sequence out of a bad one. So I will explain in a moment what I mean, but it is kind of like you have the sequence Dennis the Menace, and it's a very poorly behaved sequence, but if you have an appropriately good trained nun, or Mary Poppins, she can just extract and make out of the sequence somebody very nice, somebody very predictable, and somebody who is not going to cause trouble. And that's pretty much what's happening in analysis. You can always just take any badly behaved boy and make him behave well. So again, it's a very powerful concept, and hopefully as we go along you will see this illustrated. But first let's see how that is going to work. So let an be any real valued sequence. So the numbers a1 is a real number, a2 is a real number, a3 is a real number, etc. All those numbers are real numbers. Okay, just any sequence. Let's see what we can extract about it. So we are going to define T sub 1 to be the infimum of the sequence A1, A2, A3, A4, onwards. So the entire sequence. We're going to take the infimum of the entire set of all numbers in the sequence, and that's going to be T1. Then we're going to say that T2 is going to be the infimum of the sequence starting at 2. Right? T2 is the infimum of the same sequence where the first element of the sequence was deleted. And this is just a listing of the range. Possibly some of these, maybe A1 and A2 are the same number. But this is just the listing of the terms of the sequence. And continuing in this fashion, we will define T sub n to be equal to infimum starting n term. So everything before the n term was deleted. Etc. That's Tn. So let's make a few observations about T1, T2, T3, etc. What can be said about the relationship between T1 and T2? What happens? So you can see that the set over which the infimum is taken for T1 is a larger set than the set for which T2 is taken as the infimum, because this is missing one element. So if you have a larger set contained inside of, if you have a larger set containing a smaller set, so for instance if you have the set A, which is contained inside of the set B, then what can you say about the infimum? The infimum of the larger set is generally smaller, possibly equal, but generally smaller than the infimum of the nested set, the one that sits inside. So infimums grow as you make the set smaller. As you decrease a set, the infimums grow and the supremums decrease. So T1 and T2 must satisfy this relationship. T2 cannot possibly be smaller than T1. It is kind of like a minimum, right? So if you delete more terms, the minimum has to be growing larger. Imagine, for instance, I have 100 students in a class, and I compute the smallest grade for the class. And then I take the same class and I remove several scores from the set of scores. So I had 100 scores and now suddenly I have 40 scores. Having 40 scores necessarily means that I must have a larger minimum. That is why T1 must be smaller than or equal to T2. By the same reasoning, T3 must be larger than or equal to T2, again because we deleted one more term, and therefore the minimums or the infimums must have not fallen down. They could have potentially grown or remained the same. So you can see that this sequence, I do not know what AN is. I do not know if AN is well behaved or not, but you can see that there is some measure of a nice behavior for the little t's. The little t's are an increasing sequence. The sequence is starting from one term and going to become larger and larger. So let's write it as saying that Tn is increasing sequence. So of course, I mean, by increasing, it should not be interpreted in the strict sense. It's a non-decreasing sequence. Maybe T1 is equal to T2, maybe T2 is equal to T3, but the sequence in the very least does not go down. So in analysis, you just call it also increasing. In calculus, you call it non-decreasing, but that's not important for us. So then we can do the same thing and compute capital T1 to be the supremum of the set A1, A2, A3 onwards. And capital T2 is going to be the supremum of A2, A3 onwards. Again, what's happening is that we take this larger set and compute the supremum, and then we take the same set, remove the first term of the sequence, and we have a potentially smaller set for which we also compute the supremum. And continuing in this fashion, capital Tn is going to be the supremum of the truncated sequence where the first n-1 terms were removed. So it should be starting with an plus 1, and goes onwards. So what would you observe about the capital T's? So what is T1? T1 compared to T2, which one is larger? Again, looking at this intuition, at this intuitive picture, you can see that as the sets decrease, the supremums, the upper bounds of the sets, they just tend to go down. So therefore, T2 is potentially smaller than T1. Similarly, T3 is potentially smaller than T2. And again, we have a nice looking sequence. Capital Tn's, it is decreasing. Sequence. Now, that's very nice, but we wanted information about a sub n. How does the information about lowercase t's and the uppercase t's relate to information about a sub n? Well, let's try to fix it. So suppose we have T1. How does it compare to A1? Well, A1 is just an element in the set, and T1 is like the minimum over all the elements in that set. It's a glorified minimum, which is potentially the entire set does not have a smallest number. So for instance, for 1 over n, there is no smallest number in that sequence, but there is an infimum, there is a greatest lower bound. So that means that T1 is smaller than or equal to A1 in any case. And A1 is potentially not the largest element in that set, which means that it is smaller than capital T1. By the same argument, A2 is going to be smaller than T2 and greater than lowercase t2 and smaller than capital T2. And in general, we can sandwich an between capital Tn and lowercase tn. So that gives us, if you remember from calculus, a sandwich theorem. So you can already predict that if lowercase tn and capital case tn are going to go to the same value, I mean, they are somewhat more predictable. Capital Tn's are going to decrease to their value if it exists, and lowercase tn are going to increase to the value if it exists. So it's basically, this is the behavior. An is locked between them, and as we increase the n, that's potentially what's going to happen. And then potentially we then know something about the limit behavior of the sequence lowercase an. So the goal now is to prove the following theorem. A. If P is a number bigger than 0, then the sequence 1 over n raised to the power of P goes to 0. In other words, the limit of the sequence goes to 0. B. If P is bigger than 0, the nth root of P goes to 1. C. Limit as n goes to infinity of the nth root of n is equal to 1. D. If p is bigger than 0, and alpha is a real number, then limit as n goes to infinity n to the power of alpha divided by 1 plus p to the power of n is 0. So this says basically that exponentials are always faster than polynomials or algebraic functions. E. If absolute value of x is less than 1, then limit as n goes to infinity of x to the power of n will be 0. So now we are going to prove this. So let's first prove A. Well, to prove A, all we need to do is observe that if n is bigger than 1 over epsilon to the power of 1 over p to the pth root, then 1 over n is going to be smaller than epsilon to the 1 over p, and therefore 1 over n to the power of p is going to be smaller than epsilon. And that completes the proof. B. So B is if p is a real number bigger than 0, then limit as n goes to infinity of the nth root of p is 1. So what we can do is we can then if p is bigger than 1, we can assign the sequence xn to be the nth root of p minus 1. So then that means that xn plus 1 is equal to the nth root of p, which means that if I raise it to the nth power, I have xn plus 1 to the power of n is equal to p. So what does this imply? Now here is where we use the binomial theorem. So notice that xn, here is why we assume p is bigger than 1. If p is bigger than 1, nth root of p must be bigger number than 1. So this is positive. So we know that xn is positive, or definitely non-negative. So what does it mean? If we raise it to the nth power, by binomial theorem this is the same as the sum k equals 0 to n, and choose k, xn to the power of k. times 1 to the power n minus k. And this is a sum. Each of the terms in the sum is a positive number, right? So this would be x n to the power of 0 plus n x sub n to the power 1 plus eventually just or we have just x to the n to the power of n. So this is a sum of only positive numbers. So therefore this is bigger than or equal to n times xn. So what we have in other words, we have that the number p is always bigger than or equal to n times xn. And this is always bigger than or equal than 0. So dividing by n, we have that p divided by n is always bigger than xn, and this is always bigger than 0. So now again we apply this quiz theorem. This is a very simple limit. This goes to 0. And xn is this number, right? So that implies that p over n, that limit, let's just write it like this, at 0, which is equal to limit as n goes to infinity of p over n, is bigger than or equal to limit as n goes to infinity of xn, which is the nth root of p minus 1, which is bigger than or equal to 0. So therefore this limit is 0. This limit is 0. And if this limit is 0, then nth root of p approaches 1. So they get progressively harder. The next one is slightly harder. C. So C is asking to show that limit as n goes to infinity of the nth root of n is equal to 1. Well, again we can define the sequence xn to be the nth root of n minus 1, which makes xn plus 1 equal to the nth root of n, which makes xn plus 1 to the power n equal to n. So what can we do now? Again, this is a sequence of positive terms, so we're always adding. For each n, we're adding just positive numbers. So we have that xn plus 1 to the power n, well, this number is always bigger than or equal to n choose 2 times xn squared, because this is just part of the sum of the binomial expansion of this number, and we're always adding each part of that sum is positive. So we have this, and this number is simply n minus 1 divided by 2. Once you simplify it, it's n times n minus 1 over 2 xn squared. And this is equal to n. So then by multiplying and just shifting things around, we have that 2 over n minus 1 times n is bigger than or equal to xn squared, and this is bigger than or equal to 0. taking roots and cancelling, we have that root 2 divided by n minus 1 is bigger than or equal to xn, which is, if you recall, the nth root of n minus 1, and that's bigger than or equal to 0. That means that as n is pushed to infinity, this number goes to 0. So I'll just indicate that this goes to 0. And this, of course, also goes to 0. And therefore, by the squeeze theorem, this here goes to 0. So since xn goes to 0, that means that the nth root of n approaches 1. Lastly, we show part D. And again, each of those parts increase slightly in complexity. D. So in D, we need to show that we have, first of all, alpha is a real number, and p is bigger than 0, and we want to show that limit as n goes to infinity of n to the power of alpha divided by 1 plus p to the n will approach 0. So it will be equal to 0, this limit. So here's how we do that. So first, it's always possible to pick a number k bigger than alpha. And we can then select, once k is picked bigger than alpha and fixed, select n large enough so that n is bigger than 2k. Observe so if I take n minus k plus 1, then this number, once I subtract from it n over 2, and is bigger than 2k here, so once I subtract from it n over 2, I just will get n over 2 minus k plus 1. And n over 2 from here, it's bigger than k. So that is bigger than k minus k plus 1, which is equal to 1 and bigger than 0. And so what does this imply? That implies that n minus k plus 1 is bigger than n over 2. So what can we do now? So then what we are going to do, we're going to look at 1 plus p to the n, and we're going to find some bound for it. So we have 1 plus p to the n. P is positive, so this entire thing is positive, and by the binomial theorem, we can say that this is bigger than n choose k times p to the power of k, which once expanded, once n choose k is expanded, it will be n factorial divided by k factorial divided by n minus k factorial, and once you simplify everything you get n minus 1, etc., all the way to n minus k plus 1 divided by k factorial times p to the k. Now notice that n minus k plus 1 is the smallest of those numbers. So n minus k plus 1 is smaller than n minus k plus 2, and each of them is smaller than the number to the left. So n is the larger number there. So therefore this thing is bigger than n divided by 2, we have k copies of them. So 1, 2, 3, all the way k copies. N over 2 to the power of k divided by k factorial times p to the k. Hence, once we reverse it, we have that n to the alpha divided by 1 plus p to the n is going to be smaller than p to the k multiplied by this number reversed. So once you write it out, this will be 2 to the k times k factorial divided by here I should divide this entire thing by p to the k. So just take this thing and reverse it, and multiplied by n to the power of alpha minus k. That's this n here. So since alpha is smaller than k, this entire thing is going to go to 0. That's because n to the alpha minus k will go to 0. And this is just fixed, right? We don't vary the k. So that proves D. Finally, we prove E. That takes no effort really. So E is that statement that if absolute value of x is smaller than 1, then limit as n goes to infinity of x to the n is 0. So x is then going to be assumed to be a fixed number. So all you have then is this can be written as n to the alpha divided by 1 plus p to the power of n. So what I mean by that is, first we're going to set alpha equal to 0, and we're going to now write x. X is a number smaller than 1, so x can be written as 1 over 1 plus p. So any number smaller than 1, any positive number smaller than 1, I should say, absolute value of x, can be written as 1 over 1 plus p. So if alpha is equal to 0, then by part A, we have that this is n to the 0 divided by 1 plus p to the n. That's equal to the absolute value of x to the n. And as we have shown before, this goes to 0 by part D.